Unit 2 Review. The purpose of this video is to review the topics from Unit 2. These topics are stress-strain diagrams, Modulus of Resilience and Modulus of Toughness, Hooke's law, and Poisson's ratio. Use the time shown to jump to a specific topic. Next, let's talk about stress-strain diagrams for materials. Each material has its own unique stress-strain diagram. It is typically generated by performing a destructive test on a sample of material. Typically, the sample is pulled in tension until it fails. The force applied to the sample is measured and converted into stress. The elongation of the sample is measured and converted into strain, and the two are plotted. Here is a typical stress-strain diagram for mild steel. Note that the stress is plotted on the vertical axis and strain plotted on the horizontal axis. We can get some interesting information from the initial portion of the stress-strain curve. I'm going to zoom into the data at that point. Here is a close-up of the initial portion of the stress-strain curve. We can see that for mild steel, and many other materials that we use in engineering, we have linear behavior between stress and strain in the initial portion of the test. At the top of that linear portion, we reach what we call the proportional limit. This is the point where the material no longer behaves linearly. Just after the proportional limit, we reach the yield point. Here, the yield point is approximately 36 KSI. The yield point is a very important point to us in engineering. It separates the two behavior regions, elastic and plastic. If we load the material within the elastic region and prior to the yield point, and we release the load, the sample will return back to its original size. If we load the sample beyond the yield point, then the material will be permanently deformed. We want many of the things that we design as engineers to remain in the elastic region. That means as they are loaded under normal use and then unloaded, they return back to their original shape. Generally speaking, we don't want the things we design to become permanently deformed under normal use. So to us, the yield point is often taken as the failure point or the failure stress. There is another important material property that we get from the elastic region. That is the modulus of elasticity. The modulus of elasticity is the slope of the stress-strain curve prior to the proportional limit. We can calculate the modulus of elasticity by picking a point somewhere before the proportional limit. For example, here I've put a point where the stress is 30 KSI. The strain is equal to 0.001 inches per inch at this point. I can calculate the modulus of elasticity, which is given the symbol uppercase E, as the stress divided by the strain at the point. So 30 KSI divided by 0.001 is 30,000 KSI. This is a typical modulus of elasticity value for steel. The modulus of elasticity is also sometimes referred to as the Young's modulus. The modulus of elasticity is a measure of the material's stiffness. The larger E means the stiffer the material, or the less deflection we see under load. Now I've gone back to the full stress-strain diagram to see a few more points. First, the ultimate stress, also sometimes called the tensile stress. This is the peak point on our stress-strain curve. Here it's equal to about 59 KSI. The final point of interest here is the point in which the sample breaks into two pieces in the test. The stress at this level we call the fracture stress, and that's not particularly important to us. But the fracture or rupture strain can be a very useful value. We find the fracture or rupture strain by looking down to the strain axis. Here it is about 0.38 inches per inch. The modulus of resilience, given the symbol U sub r, is a measurement of the strain energy per unit volume that a material can absorb elastically or without permanent deformation. It is equal to the area under the linear elastic portion of the stress-strain curve, up to the proportional limit. The area is always a triangular shape. The modulus of toughness, given the symbol U sub T, is a measurement of the strain energy per unit volume that a material can absorb prior to fracture. It is equal to the area under the entire stress-strain curve. Since an equation for the stress-strain curve is typically not available, the modulus of toughness is typically found using some form of numerical integration. Next, let's talk about Hooke's law. We have two equations for Hooke's law. One for normal stress and strain on the left, and one for shear stress and strain on the right. Let's first talk about the one on the left. This equation is the equation we use to calculate the modulus of elasticity using our stress-strain diagram. Hooke's law shows us that stress is proportional to strain when we're in the linear elastic range of our material. And as previously stated, this is where we usually do our engineering design, since we don't want our products to permanently deform under normal use. So Hooke's law applies in the linear portion of the stress-strain curve. It relates stress to strain. This is very useful because we can use it to relate load to deformation in the material. The equation on the right is very similar. While not previously shown, we can create a shear stress-strain diagram for a sample being exposed to a shear load, though this is uncommon to do because it's a lot more difficult than doing a normal stress-strain test. Just like with normal stress and strain, there is a linear portion to the shear stress-strain diagram. The shear modulus, given the capital letter G, is the slope of the linear portion of the shear stress-strain diagram. Here's a problem where we can apply Hooke's law for normal stress and strain. It says, determine the change in height of the cylinder. You see we have a cylinder, it's 36 inches tall with a diameter of 4 inches. And there's a load being applied, 400,000 pounds. And the modulus of elasticity of the cylinder is given as 12,000 ksi. Let me briefly talk through the steps to solving this problem. We know our load and we know the area, so we can calculate the normal stress in the cylinder. That's going to be equal to the force over the area. Next, we'll use Hooke's law. We'll rewrite it to solve for the longitudinal strain in the cylinder. That's the strain in the direction of the load. Then finally, we'll take our strain equation, which is equal to the change in length over the original length, and rewrite it to solve for the change in length. We'll have strain from the previous step, and we know L naught, that's 36 inches. Let's go ahead and solve this. Solving for normal stress, I find that it is 31.83 kips per square inch. Then using Hooke's law, I can solve for the normal strain. I get that it is 2.653 times 10 to the negative third inches per inch. Then I can solve for deflection by multiplying our normal strain by our original length, 36 inches. And I get that the change in length is about 0.1 inches. Now, that's going to be a shrinking. We know that this cylinder is in compression, but the value for deflection came out positive. So where does the negative sign actually originate? It would be way back here in stress. The 400 kips, or the 400,000 pounds, is a compression force. So that would make our normal stress negative, that would make our normal strain negative, and that would make our change in length negative. Here's a problem where we can apply Hooke's law for shear stress and strain. It says, find the magnitude of delta from the load on the block of linearly elastic material. So this block is fixed, say, at the base and fixed to a steel plate at the top. And there's a load being applied to the plate, 1,200 kips. We want to find how much this top plate deflects horizontally. It'll be the amount delta shown. This problem is very similar to the previous example problem for Hooke's law for normal stress and strain. Here are the steps. First, we can find the shear stress in the block. We know the applied force and we'll know the area. Then we can use Hooke's law. We'll rewrite Hooke's law to solve for gamma, the shear strain. There's gamma shown in the figure. It is the magnitude of that small wedge angle. When we know that angle, we can use trigonometry to solve for delta. So I've drawn a free body diagram of the block, and I've made a cut right through the middle of the block so that I could see the internal shear force. And I've drawn it here. And shown it as V, and we can see by summing forces in the x direction that V is going to be equal to 1200 kips. To calculate shear stress, I will take then our shear force, 1200 kips, and divide it by the area. So what area do we use? The area is the area of this surface on which the shear force is acting. It will be 10 inches long and 6 inches wide. And I get that the shear stress is 20 ksi. Now I can solve for shear strain using Hooke's law. I take our shear stress and divide it by our shear modulus, which is given in this problem. G is 800 ksi. Solving for shear strain, I get 0.025. Remember, that's an angle, and its units are radians. Since it is a small angle, I can say that delta is equal to 6 inches, the height of the block, times the angle 0.025 in radians. And I get that delta is 0.15 inches. Let's now talk about Poisson's ratio. Poisson's ratio is the material property which relates longitudinal strain to lateral strain. Here is the equation. Poisson's ratio is given the Greek letter nu. It is equal to negative the lateral strain divided by the longitudinal strain. Poisson's ratio describes a material property that you've probably observed if you ever pulled on an elastic band. If you pull an elastic band, the band gets longer in the longitudinal direction. That means its longitudinal strain is positive. But in the perpendicular direction, in the cross section, the elastic band gets narrower. That is the strain that's occurring in the lateral direction. There is a relationship between the longitudinal strain and the lateral strain, and that is Poisson's ratio. The negative sign in Poisson's ratio is based on the signs that exist on normal strain. Normal strain is positive when 2 points move farther apart. Normal strain is negative when 2 points move closer together. When we pull the elastic band, the longitudinal strain is positive. It gets narrower through the cross section, so the lateral strain is negative. So lateral strain and longitudinal strain are always opposite sign, and the negative out in front just corrects it so that Poisson's ratio is always a positive value. Here's a problem where we will use Poisson's ratio. It says, determine the change in diameter of the cylinder. And we have the same cylinder we looked at before, 36 inches tall, 4 inches in diameter, and a 400,000 pound load is being applied. We're also given two material properties, E, the modulus of elasticity, 12,000 ksi, and nu, Poisson's ratio, 0.35. There are several steps we need to take to go from load to change in diameter. Let me write them out. The first two steps are the same as they were in the Hooke's law problem where we were finding the change in height of the cylinder. We're going to start with the normal stress, which is equal to the normal force divided by area, and then we'll calculate strain using Hooke's law. It is equal to sigma over the modulus of elasticity. The next step is different. We're going to use Poisson's ratio equation, where Poisson's ratio, nu, which we know, is equal to negative the lateral strain divided by the longitudinal strain. So what is the strain that we found up here with Hooke's law? Well, remember that stress is normal stress, and that's in the direction of the load. So the strain is also in the direction of the load. That's the longitudinal strain. The change in diameter is going to be calculated using the lateral strain. So we can rewrite Poisson's ratio to solve for lateral strain. The last step is to use the strain equation. Now our standard strain equation is strain is equal to the change in length over the original length. Remember, this equation is based on the distance between 2 points, and those 2 points could be the 2 points that define the diameter of our cylinder. So I can rewrite the strain equation like this. The lateral strain is equal to the change in diameter over the original diameter. We can rearrange that equation to solve for the change in diameter. It's going to be equal to the lateral strain times the original diameter. When I solve for the normal stress in the cylinder, I get that negative 400 kips, because it's in compression, divided by the area is negative 31.83 ksi. Then solving for the longitudinal strain using Hooke's law, I get that it is equal to negative 2.653 times 10 to the negative third. Now the units on both stress and modulus of elasticity are the same, ksi, so they cancel out, and I just show strain as inches per inch. Now I use Poisson's equation to solve for the lateral strain. Notice that the negative sign in that equation cancels out the negative sign in my longitudinal strain. Does this make sense? Yes, it does. When we compress the cylinder, we expect it to get wider, so the diameter is going to grow, and that is why the lateral strain comes out positive. And now I can solve for the change in diameter. It's equal to my lateral strain times the original diameter, 4 inches. And I get that it is very small, 0.00371 inches. But it does grow a little bit. This completes the review of topics from Unit 2.